Okay, sorry about that. I have to restart. Internet problems. So I have put on the website the solutions to assignment 1, assignment 2. Also put the last year's midterm and the solution, so you can see more or less what I've been asking. This year's midterm should look more or less like it. Probably a bit shorter, but I don't want to commit too much. Who knows? Maybe it takes you more time. I don't know. So last time it was well received. I hope you do well too. I've discussed a bit about. So you seem quite stressed about proofs. So let me say a few more words. So if I'm asking something quite simple, like it has like 2 or 3 steps, please make sure that you do them properly. But if I'm asking you, please inverse this matrix, then I don't take 2 pages to. So if it's inverting a matrix or computing a determinant, at some point I know that you understand what you're doing, right? So I don't want me. It's not like prove that the determinant of this matrix is that number, and you have to do 15 steps to show it. So show the main ones, like show for instance, the cofactor matrix. But yeah, at some point I'm indulgent in the fact that you don't have 2 hours or 3 hours just to do one thing. All right. So if it's a very simple thing, then please be a bit more, say a bit more stuff. But if it's very long algebraic calculation, get to the point. All right. So that's more or less it about the exam. Last questions before we move on about the exam. Yeah. There are 3 questions. So there used to be 5. Now there are 3, but 3 with A, B, C, D, yeah. So it's 3 things. So if you guess right, then you just have to study 3 things and you're good. Good luck. I hope.
Yeah, it's not like too long.
But but that's a point though. It's if be strategic. So if you think it's going to take too long and you're not so sure, skip to the rest and then go back to finish it. So maybe at some point, slow people are not going to be able to do it completely. Faster ones are going to. So that's why I'm saying too, it's not enough to just like, oh, I did it once in my life, should be good. So practice, yeah. So practice makes perfect. It looks dumb to say that, but yeah, I play a violin and I have to play it once slow and then faster and then faster, and after 100 times, then I can play it more. So it's not to that point, but still, it's I'm telling you that it helps. Okay, so chapter 7, we had just introduced. Well, we had just showed derivative rules, and yeah, some rules of derivatives. So now let's move on to functions of multiple variables and partial derivatives. So now I have a feeling that I'm going to get more and more into uncharted territory for you. So please feel free to tell me if I'm going too fast. If you don't understand, it's my job to just go back and re-explain so that we're all on the same page. So maybe partial derivatives, no, but yeah, later on, yes. So what's a partial derivative? So in a sense, it's taking a derivative with respect to a single variable inside a function. And we just imagine that all the other variables don't change. That's it. So the partial derivative measures the effect of a change in a single independent variable. On a dependent variable. Holding the other constant. So example with two variables. Oh yeah, that's right. That's going to be a war between me and the next teacher who always puts it down. So z is a function of x and y. So x and y are two independent variables. F is my function and z is the dependent variable. So how do I write them? So this I already showed you a bit the notation, but let's rewrite it again. So I show this way. So dz x. And this is, so if you think my D looks strange, well, it's because it is strange. So that's what we use when we deal with partial derivatives. So remember that. So I can write it this one, for instance, to say that I'm taking the derivative with respect to the first argument of the function. And of course, what I get is essentially a new function, which is still a function of x and y, because the derivative will change if I change the value of x or y. So I should always put it there. If I don't put it there, it's not because it doesn't exist. It's not important. It's just for some reason, I don't have time. I don't have space. I'm in a hurry, but it is always there. Except for linear functions, then it's constant. Yeah. Oh, so let me write this. Is the partial derivative of x taking y as constant. Then of course, easy. Oh yeah, and another notation that I did introduce was, for instance, if x has some special meaning, then another okay way to notice it is this way. So you would write fx. That would be good. And then the f dy, dz dy would be f2, because that's the second variable or the second argument. And you could also write dy. Well, I'm not so happy with that notation, just because sometimes you may put something else in there. So it's like 3h plus 7, for instance. That could be it. So then you say, yeah, it's f of y of, then, but then what is it? You know, it's so. But if you have a y there, then okay, it's fine. I know it's this y, as long as it's clear. With respect to y, taking x as constant. And is the, let's see, partial symbol. And of course, it generalizes to n variable. And we have something like y f of 1 n. Then I would have y psi, which I would write f I. Yeah, or or if so is it important in economics? Yes. We always use this. This is the ceteris. What is the impact on I and V holding all the other as so it's not that we think that they are always constant or they never change. We know that they change, but to say something non-trivial about the impact of something on something else, then you have to have this assumption. Otherwise, what you're saying is, yes, but I don't know because something else could happen and couldn't change my conclusion. Well, if you don't have at some point restriction about the way you study reality, you cannot study. Example, the cup blue glass. Function can be used in macro for production as well. So is that something you've heard before? Yes. Is somebody who has heard about this? Okay, good. So it's not everybody, so I'm learning, I'm teaching something to people. So it would be something like z equals x to the a times y to the. So that's a function that we use all the time for utility and sometimes for production that has nice, neat properties that make it quite convenient. Not always so realistic, but useful. So partial derivative. So I'll do one and then you do the other. So then I use my rules of derivation. So I assume that y is constant and I change it. A is a parameter, B is a parameter, and then my rule is simply that I get a x times 8x to the a minus 1. All right. And then same thing for the other. Dy. So what do I get? Yes. So same thing. Now I take x as constant and I just vary y. So the exponent is b. So I get b y b minus 1. So if you're not familiar with all the derivative rules, it's going to be painful for a while, but please get familiar with them as soon as possible. No, not so. So if you have say xy for instance. So in that case, what we don't really like, or yeah, the nice thing. So the question is, do you always need to have a plus b equals 1? So in that case, what's neat about it is you get, so if this is a production function, you get constant returns. So the goal is, for instance, then if I double the value of x and double the value of y, then I double the value of z. So that if it's a utility function, it doesn't matter whatsoever because we don't measure happiness. All we care about is the relative impact of x on y. So if then I put this to some crazy exponent, who cares? It represents the same preferences. In production, though, it does matter a lot. So, and in macro, we tend to use constant returns. Yeah. Not necessarily. Yeah. If you have good reasons to believe that returns are not constant, then yes, you. And by the way, so some macro papers actually that's what they try to do. They try to look at a country's production and input use of variable input, and then they try to fit the best production function possible. And sometimes they try to restrict to put an additional restriction that a plus b equals 1, but sometimes not. And sometimes the fit is, of course, the more freedom you allow in your variable, the better the fit. But the question is then, is the null hypothesis that a plus b equals 1 is it rejected or not? So sometimes it's not rejected. So yeah, exactly. Okay, so that's it basically. So that's partial derivatives. Very useful. We're going to use them a bunch. So please learn them. Now the gradient. So now I hope that some people have not heard about it. So who has heard about the gradient? Yeah, okay, that was my my idea. So now we're getting into less charted territory. It's not all that that complicated. It's just a mathematical object that we use for various purposes. So the gradient is the vector of partial derivatives. Of it. For a function f x And the gradient is open del f of x1, x2, xn, which is the just a vector of partial derivatives. So f. So here I'm not going to all the time put x1, x2, xn, but they're there. So I'm just going to say it's f1, f2, fn. But you know, if I was perfectly coherent, I would always put the arguments there. Yeah, so this is an object that has meaning and usefulness. Oh, and by the way, so where this thing there is pronouns. Two things, either there or nabla. And it's not really a Greek letter. So I'm not sure exactly where it comes from, but so we use it to represent the gradient. Very easy way. Oh, by the way, I'm using the same notation as in the books. I'm representing the vector in between parentheses. Okay. So what do we use that for? Well, it's especially useful for optimization. So now we're getting really into more mathy territory, but not just for that. The neat thing is it points in the direction of greatest ascent. So here I have a small drawing that I made. So it looks like this. Can I copy that there? Yes. Okay, so if you have some function, here it's a function of just two variables, x and y, and then z is the value of x, f of x, y. And then what is the gradient? Well, the gradient is this vector, which lives essentially on the xy plane, and it points towards the direction of greatest descent. So if you have, this looks a bit like a mountain. If you do compute the gradient, then, so for instance, you're here, and then you compute the gradient in that direction, and then this gives you a number and a number. And then, so it's the two of them gives you a vector, for instance. So if we're in Montreal and Montreal is like this way, so then the gradient would point. And as you can see here, the function is slightly flatter, so the gradient is smaller in magnitude, or we would say the norm is smaller. So the norm is another concept that I haven't talked too much about. Probably I won't have time to talk about it. It's basically the length of a vector. And here, since the function is steeper, then the gradient is going to give you a larger value.
Will we see normal vectors in great physics?
I don't know.
Is it ever used?
Yeah, so it's very useful in optimization. And yeah, not all that much actually. So that's why I slightly talk about it. And the next topic is, even in my opinion, I'm following the program and they were talking about it, but I have a very hard time justifying why we spent some time on it. Maybe I should just have removed it, but you know, I want to do a good job. So yeah, exactly. So, and very useful in math. So in a sense, when you do research, you want to estimate models and you optimize stuff, and the gradient is everywhere. But you know, that's not as economists, you just want to write your model and let the computer do it for you. Yeah, so just note the norm or the magnitude of the gradient is bigger, larger when is and also note here what is the value of the gradient. The optimum, the gradient is 0. That's what we're looking for when we're estimating models. I'm going to put this in a bold case because it's a vector. So what this means is the first derivative of f with respect to x is 0, with respect to y is 0, with respect to all other variables is all 0. That's what it means to be at the top of the mountain. And again, if you imagine that you arrived at the top of Mount Royal, then where should you go to ascend higher? Well, you don't know, you don't have an answer to that because you cannot ascend higher. All right. So that's all I have to say about the gradient. Just know what this is in case you encounter it in the wild and you don't want to. You want to know how to handle it. Oops, why do I have questions about gradients or about partial derivatives? Really, the thing I can ask you is, please compute a partial derivative. Please compute a gradient. So it's a recipe. Please do it. I'm the professor. I'm asking you something. It's kind of thing I can ask for the exam. Question? Yeah. So for instance, if I sit here, then what's the gradient points to this in this direction there? It means that if I go on the y-axis in this direction and the x-axis in that direction, then the value of f of xy is going to increase. And it's the direction towards which it's going to increase the most. Did I didn't? I think I didn't put an example of this, but yeah, for instance, let's go back to our example of Claude Douglas. So for instance, so imagine that I have xy. So the gradient or easy. X is going to be y, and dz dy. And equal to x. So then the gradient is yeah, I didn't put any. Yeah, okay, let's write it. F of x you see that, of course, it's a function of x and y, so it's equal to y and what? I'm sorry. Yeah, sure. Yeah. I'm following the book, but the thing with this is we're getting to Jacobians, and then we have matrices. So that's the goal of is to not change all the settings. So, and for instance, so I could have, for instance, evaluate the gradient at 1, which would be equal to. So that's that points to. So if I have my cup of glass, it's going to look like this. So if I'm at say 1, and then what is the value of the gradient? It's 1. So it's a vector that points in the direction essentially. So I can just say that I'm here and I go towards this direction there. And of course, this gives me a higher utility. That makes sense? Exactly. And of course, you can have gradients in more than 2 dimensions. It's just now impossible to see them in your head, but they still exist. Okay, Jacobian matrices, Jacobian matrix. And determinant. So who has heard of Jacobian matrix here? Yeah, one. So yeah. Don't worry, it's just a small addition to this chapter. Then we hop on the next chapter, which is much more extremely useful for economics. Okay, given m functions of n variables, the Jacobian matrix contains the partial derivative of Rn function. With respect to Rn variable. So yes, that's Jacobian. And it's named after Jacobi, famous German mathematician, I think. Yeah, Polish or German, I don't. of a vector of m gradients. And what we do with this, well, we do many things. It's especially useful for mappings. So when you have function of many variables which are influenced by many other variables. And then you want to know what happens when you take a mapping of the function. But so, yeah, now we're not going to talk about this. We just talk about the way, the fact that you can test for functional dependence. So give us a way. Test whether functional dependence exists among the set of n function, among n function and n variables. So note that here I have the same number of functions and variables. And essentially what functional dependence means that at a certain point, does the gradient point in the same direction, or can you reconstruct the gradient of one by using a linear combination of the gradients of some other function? Or do they all point to in different places? And this is useful for much more advanced math. So again, I'm not sure why they want to teach this, but here it is. So here's an example. So two variable example. So if I want have y1 equals, and then I'm going to put f1 here to say that it's the function number one, x2, and then y2, x2. So you see that I have two functions of two variables, and then each equation has first order derivatives, or if function order so for partial so the Jacobian is so you write it J. Here and so you so this is why I presented the gradient this way, f1, f2, until fn, because we're going to use rows to represent each row is going to be represented by, or each function is going to be represented in one row. And yes, what we're going to show is something like UI. One, UI1, dx2. with the export. Or you could also write it. Oh, no, I think it's better to just leave it this way. To confuse these F's is not very good. And then what do we do with this? Well, we test for a linear dependence. I think this is useful for constraint optimization. When we want to say optimize a utility function, and you have this you don't see in the book, so I'm going like further than I should maybe, but I think the usefulness of one usefulness of this in your context is, for instance, if you want to optimize utility and you have some budget constraint, for instance, then this budget constraint is itself a function. So it would be something like n equals 1. So this function has a gradient like this function, which was and then when do you know that you're at the optimum? You know that you're at the optimum when the gradient of this function is equal to the gradient of that function, or it is rather they point in the same direction. It might not be exactly equal, but if both point in the same direction, then you know that you probably found the maximum. If you are here, for instance, then the gradient of the function points this way, and the gradient of the budget constraint points this way. So if you're not at the optimum, but if they point in the same direction, then these two are going to be tangent. You're not saying more. I'm doing my best to justify what I'm showing. Yeah, I'm sure mathematicians have so many. By the way, so the Jacobian can be thought as this matrix, or it can just be thought as the determinant of this matrix. That's what they care about. Yeah, so let's just compute the determinant. So if the determinant of the Jacobian is 0, this indicates that there is functional dependence among the functions. Yeah, so what this means essentially is that x1 and x2 change the value of f1 exactly in the same proportion as x1 and x2 change the value of f2. So yeah, do I do that? No, it's different. It's just the slope of a function at a certain place. Yeah. Yeah, the thing is, what's different from this to say the linear system we had is linear system, it's easy to see that if for instance, the determinant is 0, then you cannot find a solution. But this is all is local. It's always true at some value of x1 and x2. But then if you pick some other value, then the value of the gradient changes, for instance. Yeah. Okay, let's do it for n variables. And by the way, so for you to be able to compute the determinant of this, then you need the same function, number of functions and same number of variables. and functions. The UI X. Okay. So once the first row, and 2 on the second row. So sorry for people who copy. Maybe you can just take a break if it's just too much writing. And that, and that, and some more. So that's for, you can have as many variables as you want, but I'm sure you, so the kind of thing I can ask you is please compute the Jacobian. You can imagine I'm not going to ask you for a 4x4 because it means computing 16 different partial derivatives and then computing the determinant of 4x4. You would just die along the way. But still, I have some quiz and gradients here that I'm going to share with you. Yeah, I'm going to put it on the website later. Okay, so that's it for gradients. Yeah, I would really like to be more enthusiastic about doing this, but yeah, so I can ask you verify whether it's
Yeah, maybe it's like this, because if they already think that we can have optimization.
oh, okay, in this context, yeah, well, in this so what we want is zero gradient to get an optimum.
So if they can keep it zero, then the gradient is moving the same time. The gradient of another.
Yes, exactly. It's pointing in the same direction. Yeah.
So we don't want linear independent.
Oh, oh, I see what you mean. Yes, yes, yes. So if you're looking for a solution to a constraint optimization, then yes, you're looking for that. All right, so let's move on to a more interesting topic, in my opinion. A question about this, and maybe you can ask me questions, but I won't know the answers because it's more advanced stuff. So, survival strategy: learn to compute partial derivatives, learn how to arrange them in the Jacobian, and then compute the determinant of the Jacobian. So, okay. Chapter 8. So we're moving on, and yeah, we're going to finish probably in time. Yeah, we're going to finish in time. So general function model. as I like to name it, moving the x around. So why am I writing it this way? Because dx is a small value in the units of x, so it's a small change of x. So being a small change of x, it's just a number like any other number. So you can divide by it, but you can also multiply by it and do whatever you like with it and find all sorts of interesting results with that. So do not fear what we're going to do. It's quite fun, actually. I like it. Okay. So let's start with an example. It's always best this way. So consider the equation z equals x squared plus y squared. So if I put it z squared, that's, so somebody knows this is, yes. Yeah, it's a circle. So, but I don't really care about the radius too much. So I'm just going to leave it with z. That's good enough. So it looks, if it just this way, what does that look like? Well, x squared looks like this. So if I have in 2D, then I'm going to have, this is at 0, 0. So it means that I have some other things that look like this. So it looks like a ball or a two-dimensional parabola. So yeah, it's just a two-dimensional function. That's like the simplest thing I can think of. And let's have some fun with it. So the partial derivative. Yeah, let me always be properly. F x is, so somebody else, please compute it. Dx equals yes. Yeah, great, 2x. So we have something there, and we say for now y is a constant. If you derive the constant by with anything, you just get 0. So and the derivative of x squared, then it's 2x. So what does that mean? It means that if I would increase x by some very small amount, what would be the change in z for each unit of this small amount, right? So it's a slope, it's a rate of change. But I could ask the following. We may ask. I have just a question. I'm questioning myself about my notation there. Okay, well, I'm going to write it this way. So imagine So this is just like a bridge to what we're going to discuss, but I'm going to imagine Z is only function. This is just to not bother about the partials for now. So you would just, because at some point it's just a formalism. There's really no big difference between the Latin D and these curly Ds. It's just a convention that we use. So, but I want to leave them this way. Okay, so we may ask, how would Z change following that we call dx? So this is not saying if I change x by a small amount, then per amount, how is z going to change? Here is just saying if I change x, then what will have been the change in y? So how do I do that? So let's just multiply both sides. Here I would, so dx is, it's not zero, it's just a small number. I can do whatever I like with it. So let me just multiply it by dx. So what do I get? I get that. So these two cancel out. So dx will be equal to 2x dx. dz, sorry, will be equal to 2x dx. So what is dz? It's the change in x in z that happened after I have changed the value of x by some small amount. And what was 2x here? Well, it was my partial derivative. So more generally, for any function, I would have something like dz would be equal to the by times dx. So this just means every time if I'm at some value of x and some y, but it doesn't matter here, and I change I change x by some small amount, then how is z going to change? Well, it's going to change by x, the dx multiplied by the derivative at that point. So it's just it's useful to use the board just for a very short while. So it's saying, for instance, I'm here, and now what is the derivative? It's there, and then I just say, okay, what is the impact on z? So dx, a small change in x. So it's saying essentially that I can just imagine that it's linear, and that I just have to use the rate of change. Yeah. And then what's neat about this is I can do it for all the variables that could possibly change. So if both x and y change, so I would have that dz equals dz dx plus, and then y can change as well. So dz dy. In that case, in our case, it would be 2x dx plus, and then the partial with respect to y is 2y. So 2y. All right. And now we can just formalize what I just introduced here. So total differential oh, assume the function y is function x1, x2. The total differential is this. So but here I'm just going to write just for me. Yeah. X1 and yeah, so maybe not a great idea. So df dx2 dx2. And if I wanted to really see what this means is the change that originates, that is, so the change of z is caused by two things. So it's caused by the fact that x1 has changed by a small amount, and it's caused by the fact that x2 has changed by a small amount. Hmm? Oh, yeah, sorry. Yeah, taking this was a very bad idea. Yeah, so this is the change due to x1, and this, oh, gee, sorry about that. Change in y due to x. Writing on the board sometimes is easier. So some example or other example. So if I have, for instance, y x1 squared x2, then what happens if x1 changes a bit and x2 changes a bit? So dy equals to, so do it. Take some time to do it yourself. Again, to practice taking derivatives. Okay, so most people seen them. So let's go for it. So the partial with respect to x1 is 2x1 to the 1 times the x1 plus, and then I get 3 squared. So another example, imagine you have a utility function. So it's economics because I'm going to change the letter. So u of x1, let's say consume 3 goods, x3 equals to, let's say, 2x1. So that's a very unlikely utility function, but why not? 4x3. Then I'm going to have du. So du is all the ways in which my utility can change, which will be equal to, so I'm just going to write u1 dx1 plus plus u3 dx. Again, this as arguments is just that yeah, okay, let's put them just to be sure. Then it is equal to, so u1 is 2. Right, I just take the partial derivative, so another u2 is 3, and u3 is 4. So this essentially is going to just be a local, well, actually, in that case, it's not local because the change in utility caused by the consumption of each good is always the same. Doesn't depend on the value of x1, x4, x3. That's
Are these perfect substitutes?
yes, exactly. Yeah, perfect substitutes. Another example. Maybe I can just leave it to you to do it, and then, yeah, I'm just going to, so u of x1 equals to, yeah, let's have a Code de Glace like we're used to. So 1 minus, so compute the total derivative. By the way, I know the total differential. So yeah, exactly. So, but I'm just so I'm because in the notes for some reason they change. Yeah, okay, I see what the means. So yeah, so it's always total differential, but it's the same idea. At some point, I don't want to be a stick up on vocabulary. Okay, so some rules. They look very much like the rules that we already know. Yeah, and then we are going to finish with this and continue next time. Constant rule. PC equals 0. Constant factor rule. So here I'm not taking too long to prove stuff, but yeah, it would be a neat exercise to try them. VCU equals CU. Power function rule. N equals N U N minus 1 du. Right here. Sum difference rule. V plus or minus V. Plus or minus V. Product rule. That one is famous. V equals V quotient rule. Equals 1 over V squared times V du minus U dv. And yeah, other rules are also. Okay, so that's good for today. Yeah, so I went a bit fast, but you know, no time to waste on proving all of this. So best of luck for your exam. Don't waste time, and yeah, do your best.